In this video, we are discussing hydrostatic pressure and fluid force. I think all of these little words tell you exactly what we're talking about. Hydro just means water, but it's actually the material in this section is actually going to relate to any fluid. So we've got fluid, and it's static, meaning it's not moving. So if you've got some fluid and it's staying in one place, it's exerting a pressure on everything around it. So we're going to talk about what that pressure is, and we're going to discuss the force due to that pressure on things that are under the water. So here's our first fact, and I think this is intuitively true. I think we all know this already. The first fact says that water pressure increases as depth from the water level increases. If you've ever gone diving or even just swam in deep water, you know the farther you go underwater, the more pressure you experience. And the reason for that is because the amount of water above you is increasing as you go to larger depths. So let's say that this is your water level. And let's say we've got a thin, flat plate down here. And I'm drawing it on an angle, but it's actually just like a rectangular plate almost. And that thin plate has area A. Well, the amount of force being exerted on this little thin plate of area A due to the water pressure depends on the amount of water that's above it. So it depends on this volume of water that sits above A. Now I'm going to put a little wave here to say that that's a little bit closer to us. So all of this water that's above A is acting on A. It's exerting a pressure or exerting a force. And you might ask yourself, well, how much is that force? Well, it depends on a couple of things. It depends on the density of the water. And it doesn't necessarily have to be water, it could be some other fluid. So let's say our fluid has density. That's mass per unit volume. And that mass per unit volume is represented by the Greek letter rho. So if I take that and I multiply by, volume, so that's density times volume. That's going to be mass per unit volume times volume. That's going to give me the mass back. Well, if I want the volume of water that's acting on this plate A, well, I need two things. I need A, and I need to multiply by the depth that A is at. So this is our depth. So that volume is just going to be that area times the depth. So we've got a density rho. Our mass is equal to the density rho times the volume. Density is just a property of the fluid. Somebody's going to have to give that to you. It's going to be different for different fluids. And the volume of water that's acting above A is A times the depth. We're going to use D for depth. So if I want the amount of force that's acting on this plate A, that's going to be mass times acceleration. We know that's true. You know, normally write it this way, F equals ma. But this piece is our mass. So this is equal to density times the area of that slice times the depth of the slice. And acceleration is going to be acceleration due to gravity in this case. So gravity is acting on this water and it's pulling it down. So we're going to multiply by gravity, which is G. So force, or we might say fluid force, force due to this fluid acting on A is the density of the fluid, so it's mass per unit volume, times gravity, acceleration due to gravity. Now that's force per unit volume if we multiply those together. So I've taken care of this part and this part, times depth times the area of that little piece that it's acting on. So that's fluid force. Now we're going to use this equation to define something called hydrostatic pressure, or pressure due to this fluid. Pressure is defined to be force per unit area. And I think that makes intuitive sense. Force is just some measure of the amount of push or pull that's acting on A. And if I'm talking about pressure, I want to know, well, how much force is acting per unit area? Is there a lot of force acting on a tiny area, or is the same amount of force more spread throughout a larger area? That's going to lead to a decrease in our pressure. So pressure is force divided by area, and notice up here, the area is on the end. Force divided by area is going to be density times gravity times depth. So this is density of the fluid times acceleration due to gravity times our depth below the water level, or that fluid level. And so what we end up with is mass per unit volume times acceleration. So that's giving us force per unit volume. And then we're taking that and we're multiplying it by depth. That depth is one dimension, or that's like distance in one dimension. And this is distance, units of distance by distance by distance. So this is maybe in meters cubed, and this is in meters. Those meters and that one of those meters will cancel, and what we'll end up with is force per unit area, which is exactly what we see here. So the dimensional analysis works out. We tend to write P for pressure this way. Density is rho, acceleration due to gravity is G, and D is our depth. This is nice and short as long as you can remember what all of those letters mean. And then fluid force is pressure times area or if you prefer, density times gravity times depth times area. Okay, so those are our two equations. So that's our first fact, and that first fact allows us to derive the equations for fluid pressure and then force due to that fluid pressure, provided that the fluid isn't moving. So that's why they call this hydrostatic pressure, or they should just call it static pressure and say it's different for different fluids. Okay, so that's our first fact. Our second fact is called Pascal's principle. And it says this: at a constant depth, the pressure due to a liquid is the same in all directions. I read one textbook that said, if you're talking about a diver, so here's our diver. I'm not a very good artist. There's his hair, and there's his ears. Maybe his eyes look like this. And he's happy because he's diving, right? They say the pressure at his nose is the same as the pressure at his ears. You might say, what do you mean? Well, they're all going to be, provided he's straight up and down like this. His nose and his ears are at the same depth. So the pressure is the same no matter which direction you're coming from. If you're coming from this angle, you're coming from the front of his nose, it does not matter. If he's at the same depth, if his ears and his nose are at the same depth, they're experiencing the same pressure. This is a physical principle. It's verified by experiment. And that means even if this area is not flat like this, it's not parallel to our water level like I've drawn it. So I'm imagining water up here and water up here. So we've got water, and this is an area that is parallel to that water level. That area does not have to be parallel to that water level. If it's at a constant depth, the pressure experienced by that is still going to be the density times gravity times the depth, no matter which direction you're coming from. And the force acting on something is still pressure times gravity pressure, which is density times gravity times depth, times the area of that piece. Whether that area is parallel to the water level, vertical to the water level, at an angle from the water level, it does not matter how that area is oriented. If it's at a constant depth, it's going to be experiencing exactly the same pressure. So what Pascal's principle is telling us is these formulas hold no matter how A is oriented. Okay, now before we do some examples, I do want to make a couple of notes about units. In SI units, those are our scientific units, we know force is measured in newtons, which are represented by capital N. Area tends to be measured in meters squared. So pressure, which is force per unit area, is measured in newtons per meter squared. Now 1 newton per a square meter is called a Pascal, after the same guy who came with this principle, Pascal's principle. So PA is an abbreviation for Pascal. And those are units of pressure. It's a newton per meter squared. Now in English units, we know force is measured in pounds. We know area is measured in square feet. So our pressure is just going to be pounds per square foot. That's how we'll measure it. And that's going to be good enough for us. We don't have any special name for pounds per square feet. It's pounds per square foot, not feet. Okay, so let's do some problems. Let's say you have, let's say, semicircular door in a dam somewhere. And so here's our water level, and there's a dam, and far underwater there's a dam that looks like this. And maybe they tell you that this dam is, or this little semicircular door is, let's say 6 feet across. And this is full of water. And water has a weight density. So that's force per unit area of 62.4 pounds per cubic foot. So if this is 6 feet and it's a semicircle, then we know that this is 3 feet. And it also has to have to tell us how far underwater it is. So maybe they're going to say this is all 20 feet underwater. So somebody might ask you, here's your question. They might ask you to find the force due to hydrostatic pressure, so water that's not moving, on that semicircular door. This door at the bottom of the dam. Okay. So if I want to find that force, well, we know that force is pressure times area. And we know pressure is a function of depth. So that tells us that at the very bottom of this door, the bottom of this door is experiencing more pressure than the top of the door is. And if it's experiencing more pressure, relative to area, if this is experiencing more pressure than this, then the force is going to change from piece to piece. Now remember what pressure is. Pressure is density, so that's mass per unit volume, times gravity, times depth, times area, and that pressure is changing from piece to piece. So what we need to do is we need to slice this in such a way that the entire slice is at a given depth. And then we'll find the force on the slice, then we'll add those up, we'll get the sum of the forces on all of the slices and take the limit as the number of slices goes to infinity to get the exact force. Okay, so I'm going to put an I on everything. Talking about the force on the ith slice. Alright, and if I want to slice this so that the entire slice is at a constant depth, I guess I need to slice it this way. The depth for that slice is that distance right there. And the area of that slice, well, that's going to be delta y times that distance, the distance from there to there. Now, in order to write an integral for this, I need to decide on what my coordinate system is. This time our coordinate system was not given to us, so we have to choose. And it's completely up to you, but for most of these problems, there is symmetry. There's often symmetry. If I've got a semicircular door, there's a lot of symmetry here, symmetry about this point, the center of the circle. So with that in mind, I'm going to choose my origin. This is going to be my x-axis and this is going to be my y-axis, so that the origin is at the center and the bottom of this circle. So here's a coordinate system. I'm superimposing it. You can put your own coordinate system. You don't have to use mine. But choosing to put the origin at the center and at the bottom here is going to make almost all of our equations much easier. Easier to to find. So we're trying to find the force on this one little rectangular piece. I'm going to start using abbreviations. Force is density times gravity, acceleration due to gravity, times depth times area. Now remember, this is mass per unit volume times acceleration. So when you multiply these together, you're going to get force per unit volume. Since we're in English units, gravity is already included in those pounds. So force per unit volume is that 62.4 pounds of force that is acting on 1 cubic foot. That's the weight of 1 cubic foot of water. Now I just need to find the depth that slice is at, and then the area of the slice. Now the area can be broken down even further. So I'm going to write depth here. Area is always going to be delta y times something. Now I know that this is not a perfect rectangle, but in the limit it's basically going to be a rectangle. So the area is going to be this length times delta y. And that's going to be true for all of them. So we're going to have force per unit volume, or density times gravity, times depth. All of this makes pressure. Pressure times area gives us force. Okay, so I just need the depth and the length now, and then I'm good to go. Now when you decide on what your depth and your length are, these formulas are going to be relative to where you decided that origin was. As long as you're consistent with your choice of origin, when you evaluate the integral, you're going to get the same result as someone who put the origin somewhere else. So given that our origin is right here, we're told that our water level is 20 feet from the bottom of that door. So this is y equals 20. So the depth is a vertical distance. It's the top y value minus the bottom y value. So that's going to be 20 minus the y value on this rectangular slab. So that's going to be 20 minus y. That's going to be feet. And then the length of this piece is actually pretty simple. The length is just 2 times x, because that's x and that's x, provided that y equals, or the y-axis is going directly through the middle of that door. And now I just need x in terms of y, because we're integrating with respect to y. Well, on a semicircle, with the center at the origin, we have x squared plus y squared equals the radius squared. If the diameter is 6, the radius is 3. So 3 squared is 9. So if I'm solving for x in terms of y, I subtract y squared from both sides, and I get x equals plus or minus this square root. Or you could just use the positive one and then double it to get the distance. It's going to be the same thing. So we have 2 times x, and x is the square root of 9 minus y squared. So that's my length. And that goes here. Alright, so we're almost done. That's the force on one piece. The total force acting on that semicircular door is the limit as the number of pieces goes to infinity of the sum as I goes from 1 to n. Those n forces, we're adding those together. And then we're taking the limit as the number of pieces goes to infinity to get an integral. So we're going to have 62.4 times 2 times 20 minus y times the square root of 9 minus y squared. Delta y becomes dy in the limit. And be careful here, you want to integrate where you have fluid interacting with your door. We're integrating where we're counting up that force. So we are integrating from y equals 0 to 3, not y equals 0 to 20. We're just interested in the force on this door due to the pressure of the fluid, and the door only exists for y between 0 and 3. So we get that. And this is an integral that we can evaluate. Now, there are lots of different ways to evaluate it. I could distribute this square root of 9 minus y squared here and do a u sub for part of it and a trig sub for another part. I think I would rather take advantage of geometry, so I'm going to do that this time so that I can avoid doing the trigonometric substitution. 62.4 times 2 is 124.8, and we're integrating from 0 to 3. So I've taken care of these guys. 20 times that square root is right here. And then I have a negative y times that square root. To evaluate this integral, I can do a u sub, and this one requires trig sub, but I can use geometry to get around that. So I'm going to use geometry to get around this. I'm going to split this into two integrals. Don't forget to distribute that 124.8. So I have 20 times the 124.8. It's 2496 times the integral from 0 to 3 of this square root. And then I have a minus, I'm distributing that 124.8 minus 124.8 times the integral from 0 to 3 of y times the square root. Now this, I could do a trigonometric substitution, but there's an easier way. This is like x. X is a function of y. So they're telling us that x equals the square root of 9 minus y squared. And that means that x squared equals 9 minus y squared, but we only want x to be positive or 0. So x squared plus y squared equals 9, but we want x to be positive or 0 because x was this positive square root. So we're talking about a part of a circle. X squared plus y squared equals 9, that's a circle of radius 3. But we only want the part where x is positive, so I actually don't want this part over here at all. That's where x is negative, right? And I want to integrate this function from y equals 0 to 3. I'm actually only interested in that region. Well, that's just 1/4 of the area of that circle. So I'm going to get 2496, that's still there, times 1/4 of pi r squared, and r is 3. Now, if we had done the trigonometric substitution and evaluated that integral, we would eventually get this for the area of that region, and then we'd multiply it by that. But this is much easier. If you can think of that as part of a circle, it simplifies your calculations a lot. So when I take this number and divide by 4, and then I multiply by 9, I get 5616 times pi. Okay, so that's that first part. Now this part requires a u sub. So I'm going to let u be my inside function. And my inside function is this 9 minus y squared. Now I know it's going to be a u sub because if I take the derivative of this function inside, I get negative 2y dy. Now I'm not concerned about the negative 2, I'm just looking for the y dy, and I've got a y dy right there. So I can solve this equation for y dy by multiplying both sides by negative 1/2. And then we can evaluate u at y equals 0 and y equals 3 and subtract. At y equals 3, we get u equals 0. And at y equals 0, we get u equals 9. So now we have this integral in terms of u. We've got negative 124.8 times the integral. Our new lower bound comes from substituting y equals 3 into this, or excuse me, our new upper bound. New upper bound is 0. New lower bound comes from substituting this lower bound into this. New lower bound is 9. This is the square root of u. And this y times dy, according to this, that's negative 1/2 of du. That's what we found right here. So we could divide by negative 1/2 and put a du off to the far right. So we end up out front with a 62.4 again. This is the integral from 9 to 0 of u to the 1/2 du. We need to do that. We need to rewrite it that way. That's u to the 1/2, so that we can use our power rule for antiderivatives. Add 1 to the exponent, and then divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Don't forget to plug in your 0 and your 9 and subtract. And don't forget to add this 56/16 pi from before. We're going to keep going. Oops. This is force. Force is 56/16 pi plus 62.4 times 2/3. And then we've got this right here. Evaluated at 0, we get 0. Evaluate at 9, we have 9 to the 3/2. So you're going to take the square root of 9 and then cube it. That's what that means. This is minus square root of 9 cubed, according to the definition of that rational exponent. Remember, x to the m over n is the nth root of x to the m. So I can take the square root of 9 and then cube it. Or you could take 9 and then cube it and then take the square root, but this is what's going to be more convenient for working with numbers. So I want to make it smaller first and then raise it to a power. Okay, square root of 9 is 3. 3 cubed is 27. Oops, inverted that 6 in the 1. So this is negative 27. Of course, 3 goes into that 9 times. And use the calculator for your arithmetic. No pi this time. That's okay. 62.4 times 2 times 9. Oh, it's a 56/16 over 5. Interesting. Or that's minus, because it's a minus there. And that's it. There is no pi on that term. So that is the fluid force. You might say, well, how many units is that? Or what are the units on that? Well, these measurements were given in feet. And we used the weight density, which was in pounds per cubic foot. So our force is going to be in pounds. So this is some number of pounds. Alright, so let's go back to the beginning of the problem. What did we do? We said, we're trying to find the force due to hydrostatic pressure on this door. And we realized calculus was necessary because there are different parts of this door that are different at different depths. So we wrote the force this way. We said force is pressure times area, and pressure depends on depth. It's density times gravity times depth multiplied by this area. And then we said area can be split up further into length times delta y. So density and gravity, either density is given to you and you have to multiply by gravity if you're in SI units, or force per unit volume, this weight density is given to you, like this. You put that in. Then you need to find the depth and length of a slice. Don't find the depth of the whole thing or the length of the whole thing. Don't tell me that the length is 6. It's only 6 at the bottom. You need to find the length and depth of a particular slice. That required imposing a coordinate system on this somewhere. And then once you've made that choice, you've decided that 0, 0 is right here, you have to stick to that choice. Your depth is written as y top minus y bottom relative to that choice. So that was 20 minus y. And the length, because of symmetry, because we chose to put the origin at the very bottom in the center of our little semicircular door, since that is right here, this distance is x, and that's twice x. That's x and that's x, so the whole distance is 2x. But I need x in terms of y because the width of that rectangle is delta y. So we solve for x in terms of y using the equation of this boundary, which happens to be a circle. Your equations might be different. We frequently have lines as boundaries, but it could be any curve. It could be y equals x squared. It could be anything. So we solve for x in terms of y, and now we've got length in terms of y, so we sub that in. Then the limit as the number of pieces goes to infinity of the sum of the forces gives us an integral, and then you evaluate the integral. This one would require trig sub, that's a u sub. If you do the trig sub, you're going to get the same area that we got, but this was actually much easier if you could think of it as area of a circular sector. I didn't have to do trig sub at all, but I got the same area. So we evaluated this, and we put the pieces together to get the force due to this water acting on this semicircular door, which is about 20 feet underwater. The bottom of the door is 20 feet underwater. Okay, so let's do a different one. Maybe this is your water level, and you've got a triangle that looks like this. And maybe this is 4 meters across, and this is, let's say, 6 meters. And that is 2 meters. And let's say we're underwater again, but of course we could change. It doesn't not necessarily have to be water. Let's say we want to find the force due to hydrostatic pressure. So due to water pressure, water that's not moving. On the vertical wall, that's this triangle shape. So it's vertical in that it's parallel to the water. So we're just imagining it's sitting up and down inside the water, and it looks like this. If I want the force due to hydrostatic pressure on this thing, it's going to have a lot more pressure down at the bottom because pressure is a function of depth than it does at the top. So that's okay. We're just going to have to use calculus. So if I want the force, the first thing I need to do is slice parallel to that water level. So you want to slice it so that your entire slice is at a constant depth. Because we want one formula for that particular slice, and pressure depends on depth. So we're going to do this. Okay. Now I'm going to label my depth and label the length of my slice. And this is a representative slice, so it's the ith slice. We assume that there are n of them total. So the depth is the distance from here to here. And the length is the distance from there to there. Now, if I want to find the force on this triangular slab, I have to use the fact that force equals pressure times area, and then break it down into a bunch of pieces, all of which we know. So our force is pressure times area, and pressure is density times gravity. It's acceleration due to gravity times depth. This is a property of the fluid. Acceleration due to gravity is a product of the, or a property of the planet that you're on. And then depth is dependent on the picture. It depends on how far underwater that little piece is. So this is all pressure, and then we're taking that area and we're breaking it into two pieces. It's going to be length times delta y every time. We're going to assume that it's a rectangle, even though it's really technically a little trapezoid. In the limit, it's going to be so small that we're going to think of it as a rectangle with dimensions length and delta y. Now, I didn't give it to you this time, but the density of water, I would have to give that to you for a test, is 1,000 kilograms per meter cubed. So I'm going to write 1,000 kilograms per meter cubed. That's my density. Acceleration due to gravity is 9.81 meters per second squared. Depth is something I need to find. Length is something I need to find. And delta y is still there. Now, depth and length are found relative to our choice of origin. So we need to decide where the origin is. Whatever you decide is fine. You just want to be consistent with that choice. So we've found the formula, or stated the formula for f sub I. And now we know we need to find the depth and the length relative to some origin. So we're going to choose an origin. And then you have to stick to that choice. Now, it's completely up to you, but you always want to choose your origin to make finding the depth and length, the depth of this slice and the length of this slice, as simple as possible. So I am going to choose to put my origin over here. I'm going to make that the positive y-axis and that the positive x-axis, because then it's really easy to find the equation of that line. It just has a y-intercept of 0, passes through 0, 0. And it's also easy to see what that depth is. Okay, so let's look at the depth. We've chosen the location of the origin. Now we want to find the depth and length relative to our choice of origin. Now, if you put your origin over here, that would work just fine too. That's an equally good choice. That corner would be fine as well. But to simplify the equation of the line, I'd probably put the origin here or here. But if you put your origin in a different location, that is totally fine. Your equations are going to look different from mine, but the value of the integral will be the same. So I'm just choosing to put it there. Now I need to find my depth and length given my choice of origin. Okay, depth. It's still vertical distance. So it's the top y value minus the bottom y value. We can never really get away from that. If it's vertical, we're going to do that. Now, given our origin, that water level is at y equals 2. Okay. So the top y value is 2. And the bottom y value is just y. Now, I've had students argue with me about this. They say, how could that possibly be y? Y is negative down here. Well, let's think about it. When y is negative 2, what's the depth? It's going to be 2 minus negative 2. The depth is going to be 4. When y is, let's say we're here, when y is negative 6, it's going to be 2 minus negative 6, or 2 plus 6, which is going to give me an 8. So the depth is the top y minus the bottom y, which is 2 minus y, and that's going to be in meters. And the length is the distance from there to there. Now length is a horizontal distance, and this is going to be the case with all of your pictures. Your depth is going to be vertical and your length is going to be horizontal. So we've got x on the right minus x on the left this time. And because there was no symmetry, this is a little bit more challenging to calculate than the last one. With the last one, because of symmetry, the length was 2x and we just needed to find x in terms of y. This time I've got x on the right minus x on the left. It's still not too bad. Let's think about it. What is x on the right? That right side, on that right side, x is equal to a constant. That's 4 units from our origin, so that's x equals 4. So x on the right is just 4. Now x on the left is the x value on this line. So I'm just going to write x sub I, but we know we need x in terms of y, but on that line. So to find x in terms of y on that line, first I need y in terms of x on that highlighted line. And once I know what y is in terms of x, I can solve it for x in terms of y. It's actually not too bad at all. Look at the line. It passes through the origin, so we're just going to use the slope formula. The slope is rise or fall over run. So it looks like we go down 6 and run to the right 4. So down 6 and over 4 times x. That is our y. We can simplify that. That's negative 3 over 2 times x. But I don't want y in terms of x, I want x in terms of y. So I need to solve this equation for x. So I'm going to multiply both sides by 2, divide both sides by negative 3, oops, and we get x is negative 2/3 of y, which is what I get if I multiply by the reciprocal of that on both sides. So if x is negative 2/3 of y, the length is 4 minus negative 2/3 of y. So that's 4 plus 2/3 of y. That's also in meters. So I've got meters cubed canceling with these meters, and these meters. These are delta y meters. So I have a kilogram meter per second squared. That's going to be a Newton, which is good. We're trying to find force. So that is, this right here is the force on one piece. That's how far we've gone. We're right here. Now if I want the force on the whole thing, I need to take the limit as the number of pieces goes to infinity, set up the integral, and decide on the correct bounds. So we found the depth and length given the choice of origin. We substituted those in. Then your next step is to state that F is the limit as the number of pieces goes to infinity of the sum of the forces on those n pieces, and that's an integral. Okay, so let's do that last step. Force is equal to the limit as the number of slices goes to infinity of the sum as I goes from 1 to n of the F sub I, the force on each individual piece, and that's going to be 1,000 times 9.81 times the integral of 2 minus y times 4 plus 2/3 of y. Delta y becomes dy in the limit, and we're going to integrate from one y value to another. Now to find the bounds for this, you want to go from the smallest y to the largest y, but you're just looking for the y values on that slab. You're only adding these up for the y values on that triangular wall. Well, it looks like this is 6 meters from that water level. So y is going to go from -6 to 0. Or that's not 6 meters from water level, it's 6 meters from the bottom of the triangle to the top. And we put the origin on that part of the triangle. So y goes from -6 to 0. Don't go from -6 to 2 because there's no triangle there. The fact that we're 2 meters under that water level, it doesn't start until there, is taken care of by the depth in our equation. The limits of integration refer only to the original region itself. So we've got -6 to 0 here. And that's easy to evaluate. You're just going to distribute. And we could take this and multiply by 1,000. Move the decimal 3 times, right? First times first is 8. Outer times outer is 4/3 of y. Inner times inner is -4y. Last times last is -2/3 of y squared. And if you want, you can simplify before you anti-differentiate. I've got 4/3 of y minus 16, or no, minus 12/3 of y, because 4 is 12 divided by 3. So 4 minus 12 is -8. So this is -8/3 of y minus 2/3 of y squared. And we're integrating with respect to y. So let's anti-differentiate. This is force. Oh, I'm so sorry, guys. There it is. Okay. Antiderivative of a constant is the constant times y. Bring the 8/3 down. Add 1 to the exponent, divide by the new exponent. Bring the 2/3 down. Add 1 to the exponent, divide by the new exponent. Plug in 0, plug in -6, and subtract. Now when we plug in 0, we're just going to get 0. Nothing happens there. When we substitute in -6, we're going to get 8 times -6. Half of 8/3 is 4/3. So that's 4/3 times -6 squared minus 2/9 times -6 cubed. So we have 0 minus this. So we have -48, -3/4 times 36. 3 goes into 36 12 times. And this is going to be -2/9 times 6 times 6 times 6. What is that? I'm not even sure. I'm just going to say 36 times -6. 9 goes into 36 4 times. And so we've got -9,810 times -48 times minus 48, and that's a -8 times a -6. That is a positive 48. So those reduce, and you end up with this 9,810 times the negative 48. Which is this number. These are not proper significant figures. But let's look at our units. Distances were given in meters. Density was given in kilograms per meter cubed. In that case, our force are going to be in units of newtons. So that's the force acting on that little triangular piece due to the pressure of that water acting along that acting on that triangular piece. Now every problem is a little different. On this one, we had to find the length and the depth. That's always going to be the same. On this one, we had to find the length and the depth. But the length here, because of symmetry, was just 2x. I needed to find 2x in terms of y. And in this case, x in terms of y was solved, or was given by the equation of this circle. So I had to take the equation of the circle and solve for x in terms of y. Now on this one, the length was just a rectangle. We had x on the right minus x on the left. And on the right hand side we just had a constant for x, but on the left hand side we had to solve for x in terms of y on this line. The geometry is going to be slightly different on every problem. This one was a circle, this one was a line. There are a lot of trapezoids in the homework. It could just as easily involve a curved boundary like y equals x squared. But make sure you understand the process. If I'm trying to find the fluid force due to some fluid acting on some surface like this, we slice so that the entire slice is at a constant depth. Then you label the depth and the length. Depth is not the same as distance from your work problems. Depth is always measured from water level. So you do top y minus bottom y to get the depth, x right minus x left to get the length, and all of those are all those formulas are based on your choice of origin. So you want to put your origin somewhere in here so that the equations of these curves are as simple as possible. Like that choice of origin made this line very simple. This choice of origin made the equation of that semicircle very simple. Once you find the depth and the length, you substitute into this formula. These two numbers, the density and acceleration due to gravity, or possibly weight density, those are going to be given to you. Those are properties of the fluid and the location where you're doing all these measurements, like Earth. So those are going to be given. What you need to find are those two pieces. Then you take the limit as the number of pieces goes to infinity, you add those up, those define an integral. And then you evaluate this integral using the fundamental theorem of calculus and all of those techniques that we talked about when we learned about anti-differentiation. So there's no product rule. So you have to distribute so that you can use your basic rules, use substitution, integration by parts, and those other methods that we discussed in the last chapter. So that's it for fluid force, guys.